Hello everybody of YouTube. Today we're going to be writing a Tetris clone in Rust using a minimal set of libraries including SDL2 and CGMath. I'm going to be using Visual Studio Code. This is going to be a stream targeted more towards intermediate Rust students, not necessarily people who are just starting out. If you're just starting out, go read the book. It's really, really good. This is more for people who are looking to expand their understanding of Rust as a language through more intermediate, medium-sized projects, which is a very difficult thing. And I think there's a real deficit of that on the internet, so I am contributing by making some more. We're going to be working off of a design document today, which is going to provide us some nice clarity into how Tetris is actually supposed to work. This was a leaked design guideline from 2009, which was provided to third-party developers when they are developing a Tetris game so that they can have a more consistent game feel for what actually is a Tetris game. It provides a lot of really interesting information, such as the timings and the points and the way that the pieces should move and the way that the game should progress. I've made a couple of Tetris games in the past, and I have a good idea, I think, of how I want to structure this. So I think we're going to just jump in and get some of the base framework started for this application before we jump into some of the more nitty-gritty details in this document. The design pattern that I'm going to try to use for this, I know there's a lot of design patterns, but the one that I found works really well for Rust is to have an engine that exposes an outward API, and then an interface layer which operates upon that engine. So basically, the way that you want to think about this when you're starting out is you've got a class which represents the game, and then you could play the game by just writing a bunch of lines of code which go through and say what inputs you're providing to the game. But the thing that you would want to do when you're actually producing a playable game is to write a wrapper around that, which automates the process, takes input from the player, processes it through the game engine, and then has a view of the new state of the world. That works well for smaller things. For larger games, you probably want to use a more established game design pattern like the entity component system, which is used by most modern game engines, especially if you're doing stuff in 3D or stuff that's really, really complicated. But this is going to be nice and simple. So to jump in and get started, first thing that I'm going to do is I'm going to make, I know that I'm going to want a module for my game engine and a module for my interface. And I know that I'm going to probably be making a lot of files underneath those, so that I'm going to start by making those as folder modules. We're going to have a module for the engine. And then inside that, we're going to make the mod.rs, which is the module file name. If you were making a module outside, of course, you would just name it engine.rs and then pull it in through the main. So here I'm going to pull in engine, and then I'm going to have a mod interface. And so I'm going to use Rust Analyzer to, oh, no, don't want to do that because that creates a file module. I wanted to create a folder module. Why is it highlighting like that? Okay. See if that fixes it. It'll be fine. I think it's just a weird highlighting thing. So in the engine, we're going to dive right into it. I want to make a structure. The engine. And I'm not going to put anything in it for now. I think it's a really good way to go about, if you have a vague idea of what you want to do, it's a good idea to declare the types that you want and then start writing the behavior that you want as if the type already represents the thing. So going to start our implementation. It's always good practice to have a new function. Although in many places you can eschew it if you have a default function, as long as you document it well. Yes, we're currently laying the main structure of the application and the way that it's going to be representing the data that it's responsible for. So we have a function new which returns a self, which is how Rust it's the Rust version of doing constructors. So here, because engine is a unit struct, we can just say engine, and it's an instance of that struct automatically. Another thing that I like to do right at the beginning of a big project is change the project attributes to allow dead code and unused let's see, where is it? Do they have one that's just for arguments? No, dead code will be fine for now. Otherwise, your compiler output is just flooded with a bunch of unrelated statements that you don't really care about for the thing that you're doing, and there's going to be a lot of dead code when you're first starting out because it's not going to you're not going to be doing the things that you're writing. So I think I'm going to be sticking pretty close to the way that I don't know if I'm going to be implementing this basic game flow chart, which has like a legal screen, title screen, main menu, and then goes from there. I think I might just jump directly in. That's all stuff that can very easily be added later. And that's one of the benefits of separating out the engine into the game portion and the interface portion, is you can very easily dictate the overall flow of the entire lifetime of the application within the interface layer, and then leave the game engine layer to be just responsible for a single playing of the game. This document also outlines what the screen should look like, which is going to be great for when we're doing the actual interface design, because it'll give us a nice solid base to build upon. So currently I'm looking for the spec talking about the game, the actual like physical layout of the game. And there are a lot of variations, but I think we're going to be sticking mostly to default stuff. Over conditions. Let's see if we can just go to do they not? Where's the section for that? Here we go. New game and interface. So matrix is the area. Oh, let's go into the matrix. The standard matrix dimensions are 20 cells high by 10 cells wide. Okay, I think that's a good thing to stick to. So in our engine, I'm going to create a new const attribute, which says that the width, which because consts need to have a type, we're going to give this a type of usize because we're going to be using it to index. That's 10 cells wide. (20 cells high). So inside the engine, we will need to we will need to keep track of a board. And I think given the types of operations that we are going to be doing on the board, I think the board deserves its own structure here. So I'm going to just put this, I'm going to put this on in the same file as the engine, and then move it to a separate module once it grows big enough to warrant its own module. So we're going to have a struct, and I think those width and height might also get moved down here. I'm not sure if... let's see. I'm not sure if struct definitions are allowed to reference constants in their own impl blocks, but if not, we can just move those to a global constant. That's fine. We're going to make this a tuple struct with a single member, which is an array of cells that is going to be... For now, I guess we can just represent them as bools and then migrate later. We're going to make it self width, self height. Let's see if this complains. Oh my god, it didn't. That's incredible. Cool. So I know now that our engine is going to at least have one member, which is a board. And we can, here, because bools derive default, we can derive the default trait, which, and the default, what does it say? Oh, default is one of those that hasn't been extended with const generics yet. If at any point in the future you are watching this video, go check to see if the default trait has support for const generic arrays. Otherwise, you're going to have to do what I'm doing here. But if it does, then you can just derive default and it'll be great. But it looks like right now I'm just going to have to either manually implement default or write a constructor, and I'm more partial to writing an explicit constructor. So we're going to make a new function called blank, which returns a self, and we're going to return a self with a bunch of false in it, and then we're going to have it derive. Does it not allow that? Left side of an assignment expression. Guess we can just do... Yes, Prosper, we are having fun. I don't know if count is it should be size. There we go. There we go. So now that we have that, we can add the initializer for our constructor here and say that board is a board blank. Yes, behave or receive moderation. Let's see. So we don't need to make any of the members of board public because they're just going to be exclusively operated on by the engine. We're going to use the engine as a proxy for the actual board. So we have a board, or if we have a game engine here, really? Okay. Oh, it's because it's not public. You to publicize. Port. It's private. Sure. Pub. Right. So if we have a game engine, we can either pretend like it's playing and do things like engine.new piece manually, but when you're actually playing, the thing that's going to be doing that is the interface. And so in the interface, we know that we're going to have an interface, which is going to have at least an engine. And I found that the vast majority of the time, you basically just have one function in a class like this, which is just says go, and that can return an error, or it can be divergent, or it can return the score or whatever. But for here, I'm just going to have it return unit. And so in here is where we will do things with our game. And so we could either have the interface construct its own game engine, or we could pass in an engine that's been pre-prepared by the main function or the test or whatever is running. And I personally like that pattern a little bit better. So I'm going to say takes an engine, moves an engine into itself, and then it will construct then we still have the to-do run the game. So then in the main, what that looks like is interface will run the engine. We're going to say import this interface. So now if we run this, oh yeah, I also named the project TETRIS to avoid copyright infringement. So if we run it, yes, it gives a warning that that's unused, and we know. But it won't be unused if we drop it, which is what's going to happen at the end of the loop anyway if it doesn't exit or no, if it does exit otherwise. Yeah. All right. Panicked, not yet implemented. Run the game. Cool. Exactly what we wanted. So, the Russian police. Oh my God. Let's see. What next? Another thing that we know we're going to need are pieces. And I know that pieces are going to be complicated enough to deserve their own file, at least. So I'm going to create a new module piece, have it automatically create it. Where did it create it? Oh, this is an interface. Nope. I wanted to create that in the engine. Oops. So in here, we can define a piece, and I know that a piece is this is our first like actual design choice that we're gonna have to make here. A piece is one of these 1, 2, 3, 4, 5, 6, 7 pieces, because these are the only 7 arrangements of 4 blocks. Of course, tetra meaning 4, tetris, tetrimino meaning 4 pieces. So we could either have a set of templates and then have a piece be comprised of those 4 and have 4 sets of coordinates inside that represent the block, or what we could do is just have a global set of pieces which are defined, and then each piece instance will reference one of those layouts. And I think I like that one a little bit better. We'll see if implementing some of the other features makes that a bad design decision and then change it at that point if it is. But for now, I think what we want to do is just have an enumeration, which is the type of piece. So this is going to have at least a kind. And we're going to have I'm going to make this public to only the super module, which is the module directly above. Then we are going to create a enum kind, which has square, line, T, L, J, S, Z. So, which version would make it easier to add new pieces, or is that irrelevant right now? Say if you want to cross piece. That is not currently relevant, both because it's fairly easy to make new pieces. Either way, it's about the same, and then also it's physically impossible to make any different pieces than these. So I think we're pretty covered on that front. So simple kind, and then we're going to say, so we want to encode the layout of these pieces. Let's take a look at the documentation a little bit closer. See what is being asked here. Random generation Tetris uses a bag system to determine the sequence of tetraminos that are during the gameplay. Okay, so int or engine, we're going to need a bag. And that is probably going to be a vec of piece. Or actually, piece kind. Not the full piece. And here what we want to do to differentiate, because we named it something really generic, which is kind, which makes sense in the context of just having the piece and then the module piece as a kind. But if we export that anywhere else, that's going to be really ambiguous. So what I'm going to do here is import kind as piece kind, and that will have an alias in this scope where it doesn't actually import kind, it only implements it as piece kind. So given that we have a bag of kinds of pieces, we know that we're going to need to be able to somehow construct a piece from a kind of piece. And that's going to have a little bit of additional information because the piece is going to also have attributes like its rotation and its position. And so here we're unable to we're unable to implement the from trait to infallibly convert from a piece to from a kind to a piece because we need additional information. So we could either make a from implementation of a tuple of all that information, or we could just have a constructor for piece, which is, I think, what I'm going to do. So I'm going to make a constructor here, which we need to know what kind it is. And then that's going to also have a position, which I'm not going to specify yet. And it also needs a rotation. And given what I've read so far about rotations, it's probably going to be beneficial for us to implement our own representation of rotation, because it's got weird stuff that goes on once you get into the super rotation system, which is what they implemented to handle some of the weird rotation stuff. So piece has a rotation and that returns itself. And so this is just going to be a... Well, I mean, given that this is all just, so far, just the information that we know is going to be in here, we actually could just publicize, because this doesn't have any invariants that it needs to hold. If you're working with a type that has implicit invariants that it needs to hold, such as for string, having the size field always be less than the capacity field, and you need to make sure that that never gets validated for the purpose, or invalidated for the purposes of memory safety, that's something that you definitely want to log behind an interface. But if you're using things like this, which it doesn't really matter, it just changes the way that the piece is. And of course there is something to be said about, you know, having the coordinates of this piece constrained to always be inside the board, but I don't know if that's something that we want to handle at this level. But other than that, disregarding that, it is appropriate here to just make all of the members of the piece public so that they can be seen and interacted with by any calling code. And here, I'm going to be using a third-party library to represent coordinates, because it's kind of a pain in the ass to try to implement all of the arithmetic that's needed for adding and subtracting vectors when that already exists, and it's really nice, and I don't have to implement rotation matrices and all that dumb shit. So we're gonna just use the CG math implementation, but I don't know exactly what those are called off the top of my head, so I'm gonna leave them blank here. And I'm going to get rid of this because we no longer need it. So this is going to have, let's look in the controls. No. Where does it start talking about this super rotation? Super rotation system. Appendix A. Super rotation system. North, south, east, west. And because those are pretty standard acronyms, I feel comfortable just using north, south, east, west as NSEW. So that has there. I guess I should actually look that up. Latest version of CG Math Crate. Traits, we want the structures. So got a vector 2, which is I think the one that we want. Vector 2 being of SC, that's nice for things like extending to GPU. And then for the implementations, okay. It's just using it as a standard generic parameter. I didn't know if they had their own like numeric type. Or no, they do. Base num. There we go. Yeah, this is the way that CG Math works. A lot of the structures and procedures are implemented based on this base numeric trait, which I think just has a lot of information for the compiler about what numerical operations can be performed on these. So That's pretty straightforward. So we're going to use a vector2 and implement and pull that in from CGMath. And here we could, if we were pressed from memory, I would use something like a U8 because the U8 min or the U8 max is way bigger than anything that a reasonable person would do on for a matrix for Tetris. And of course, if you wanted to have a super huge Tetris, you would have to bump that up. But we are not really pressed for memory here because we're not writing this for an embedded system. And numerical operations on large register size types are just about as fast as, or I don't know if it's guaranteed, but they are as fast as numerical operations on smaller types, at least for x86. So for here, we're just going to use the full register size type for the position. Two does notate the dimensions of the vector. So in the in this library is specifically for doing math related to computer graphics. And here we're talking about where we're putting things on the screen and we're rotating them. And so they've got a lot of different helpers. They've got points in 1, 2, 3-dimensional space, vectors in 1, 2, 3, 4-dimensional space, matrices representing operations in 2, 3, and 4 dimensions. Euler and quaternion operations, lots of really, really cool stuff. And then a lot of really nicely implemented extensions on top of those sets of types so that you can do fancy things that you want to do with them. So here we're making a 2-dimensional vector representing the position of the piece. And so if once we're here and we have the piece, we have the set of pieces that we're going to pull in next. We know that it's going to be able to make that from the kind of piece because it knows the position and the rotation that it wants to put. So for this logically leads to two different operations that we know we want for the engine, which is refill bag, which is going to take a mutable reference to self because we are modifying the members. Going to drink if we have to transpose a matrix. I don't think we're going to have to transpose a matrix. But we will have to refill the bag of pieces because it starts out empty. And it, of course, will be empty at some point. So we've got the bag implement self, so we can access the bag mutably. And then I don't think that takes any other... Self. I don't think that takes any other information because it just uses the random number generator, which we're going to put into the engine. So here... we will also need a random number generator. So I will need to... the rand crate, 0.8.4. Add that to the cargo toml. .8 is fine. I don't care about breakage from minor versions. So here, the important thing that we want is we need a random number generator, and it doesn't really matter too much the cryptographic security of our Tetris pieces. So the default random will be fine. Here, I know the operation that we're going to be doing is shuffling a vector. So I'm going to be looking for shuffle, which is in slice random. So the requirements for shuffle are that R does not have to be sized. R is an RNG. This is implemented on things that are Can you shrink down so that I can see? Slice random for slice of T for all of these. Implementers. Where you take a mutable reference to the slice. Okay, yeah, that makes sense. Cool. So the thing that needs to be passed in here is the RNG. Let's see if it gives in the like top one. RNG is thread RNG. What does thread RNG return? Thread RNG returns a thread RNG. That's fine. Yeah. So I know that our engine is going to need a thread RNG. We could make this generic and have the engine be generic over multiple types of RNG, which would be useful for if we were doing unit tests where we want to rely on a specific generation order. But in that case, I think it's more appropriate to explicitly state that and then be able to build in a feature where you can provide your own specific bag of pieces or your own specific ordering of pieces. And that should be implemented at a higher level than trying to hack it with a predictable RNG. Do all pieces generate with the same probability? That is a good question, and I think they talk about that in the design guideline. Tetramino generation. Size of amino is the same size as a matrix cell. Bag. 7 different tetraminos are placed in a virtual bag, shuffled into a random order. Yes. So the way that it does is it just takes a list of all 7, puts them in a bag, and then shuffles it evenly. Refilled and shuffled when it's empty. Oh, and the other thing that this has is a next queue. So in addition to the bag behind the scenes saying what is going to be pushed up next, you also have a queue of next pieces, which is visible to you, and that's in a deterministic order. And typically that is shown, let me see if I can find a picture. Yeah, it's shown as going up the side of the screen. So that one is going to be a vec deck. I think, well, I don't know. We'll get there when we get there. So, all we need currently is just the standard random, and I think thread random is perfectly fine for our purposes here. Thread RNG. So then when we refill the bag, what we want to do is put all pieces in bag, shuffle bag. So this second step is easy. That's just bag.shuffle. So you have the bag of equal weighting and then the queue of picked pieces from the bag. Yes. So this error says, no method named shuffle found for struct vec of kind. Following trait is implemented but not in scope. Perhaps add a use for it. Ruse rand prelude slice random. So that is what we want. Which will provide our extension methods that we want to use. And VS Code, of course, has an automatic import for that, but I want to do it manually at least the first time. So here it's no longer complaining. This is what we want. That is the intended behavior. Now, here's another decision. Put all of the pieces in the bag. In other languages, you would accomplish this by having all of your kinds of pieces be runtime reflected, and so you could look at the enum and then have it list all of its own variants in a row, which works for a lot of systems, especially systems that don't have algebraic data types, that don't have sum types. where that is a little bit more problematic because you need a way to indicate what the variant is without providing any data. But because Rust has algebraic data types and each variant of the enum can contain some different amount of information, what you have to do here is have a list of all of the different variants, which I'm going to represent as an array of self. Let's see if it allows me to do this. Maybe it will, maybe it won't. And this is just self square. T. Pub const all. S self Z. And it doesn't like that. But I know there are 7. Why doesn't it like that? Because it wants that syntax. No, it does want the explicit 7. All right, so now we've got a static array of all of the different variants that we want. And I know that we're going to be cloning this. S-elf stands for shelf elf. No, it does not. Derive. Clone and copy traits because there's no data here to screw it up. I also, while we're here, want to implement debug and partial equals. Debug is great for trying to figure out what's going on, and partial equals is great for when you're writing unit tests because you can compare the expected output to the actual output. And without partial eq, that's a lot harder to do. You have to rely on pattern matching. It's bad. Yes, Rust is very, very explicit. And that is the thing that trips up a lot of people when they're first starting out because they're used to languages being a lot more implicit. But the problem is when you're using an implicit language, once you get to those corner cases, it's a lot harder to figure out what's going on. And you're often surprised by the things that failed because they weren't even on your radar for things that could fail. So for instance, Rust doesn't automatically implement sortability for floating point numbers because the standard for floating point numbers has unsortable values, including nan, negative nan, positive infinity, negative infinity. And there are some weird rules regarding how those relate greater than or less than each other. And it is really complicated. And so Rust makes you actually dictate exactly how you want those edge cases to be handled. And that's a little bit off-putting to people when they first start. But in the long run, it is very, very beneficial. Trust me. So here, now that we have the array of all of our different variants, it becomes pretty easy to put all of the pieces in the bag. We say self.bag.extend from slice. Then we have piece kind all. Extend from slice. What are the requirements for extend from slice? Extend from slice requires clone. It clones. But where's the actual... Extend from slice. Where are the actual... Rate requirements on this, though? That's weird. It says in the documentation that it clones all of the elements, but I don't see any explicit requirement for the clone trait to be implemented for T. Oh wait, no. I was blind because it was directly on top of it. Implement for where T is clone. There it is. Okay, cool. So all we have to do is make sure that piece kind is clonable, and then we can extend it from the slice. So currently piece kind all is an array, and we need to take it as a slice. You can do that by either putting an ampersand in front to take a reference, and then the deref rules, because arrays implement deref to a slice, will automatically work. But I prefer to do as slice to more accurately indicate to the reader what exactly is happening here. So what this will do is it will take the bag, put in all of the new pieces, and then shuffle it. This is still string beats, yes. So here, because this is a private method, we can kind of rely on ourselves to only call refill bag when the bag is already empty, because it's going to happen in the same scope. It's easy to keep track of. But a good practice to do would be to have a debug assert, which is only enabled for debug builds, that self.bag.is empty. And then that will crash the program if that's not true, if we somehow screw it up. Pretty simple. Well, thread RNG. This is complaining currently because we're missing the RNG field of this structure. And thread RNG is really easy to acquire. So there's no special information needed, so it doesn't really make sense to put it as a parameter of the constructor. So I'll just say RNG is a thread RNG, which is a top-level method that Rand comes with that just acquires a thread RNG lazily initialized. So don't have to worry about any of that stuff. I don't know if this is not still string beats. Thank you. No, so if the bag, the debug assert means that it asserts that it's true. So we are asserting that the bag is empty, otherwise crash. Now, that's going to be something that is pretty easily relied upon, because only engine can call refill bag because it's not a public method. And so we can make sure with our eyes that we are only calling it in cases where we know that the bag is already empty. But it's a good standby to avoid really confusing situations when there's something going wrong and it's this invariant that... This is a good example of an invariant. We want this invariant to hold that refill bag can only be called when the bag is empty. And there's various different ways to assert that in the type system, but they're all very complicated. And this is simple enough that I trust it to just be doable with this debug assert, which will crash if that's not the case. And then from there, you can work backwards and say, oh, why was the bag not empty? And you can start solving the actual problem rather than trying to figure out what the problem is. So... what next? What do we still need? Now, if we really wanted to get fancy, what we could do is we could have a separate implementation for the bag, which contains the RNG, because I don't think any other part of Tetris relies on randomness. And that may be what we end up doing down the road, is packing these two into their own thing with its own behavior and its own invariance. But for now, I think it makes sense to just keep it inside the engine. The other thing that this engine needs is apart from having the actual matrix of pieces that are on the board, it will need to have a cursor that the player is currently keeping track of and manipulating, which represents a piece that has not yet been placed upon the board. And that will be interacting with the board. It will be blocked by the pieces that are on the board, but it doesn't necessarily have to be a part of the board because none of that other stuff has to interact with it. It's a one-way data flow. So they don't need to be siblings in the graph of data here. So we have a separate cursor, which is alongside the board instead of alongside the pieces on the board. The things that we need to represent with this, it's just the piece that we implemented before. So it's its own piece that can be manipulated independently. And the only difference between it and the other ones are the way that it's rendered. Yeah. So, but here's the trick. The board does not always have a piece in the cursor, I don't think. There is a state where the cursor does not exist yet. Is that right? Let's check and see if the design document has anything on that. Flowchart. Where's that one flowchart? There's a really good flowchart. There's one. Generation phase into falling phase, completion phase. Yes, the outline, there's two separate aspects to that. There is currently the piece that the player is controlling, and then there is the outline which shows where the piece will land. And those are going to be separate things, but the only one that's real in terms of the game is the one that the player controls. So I'm going to start with that, and then after that I'm going to build on the projection of the piece down onto the place where it would fall. So there's this one. I'm trying to figure out currently if at any point during this flowchart there is a place where the player's cursor will have no data in it, will not exist. Animate. The only time that would really happen is immediately after, in the lock phase, and then all the stuff happens. Goes through the completion phase. Because yeah, in the lock phase, the piece is taken out of the cursor and placed onto the board, and then it waits until the generation phase to put in a new one. So between the lock phase and the generation phase, it logically is empty. So it does make sense for this to be an option of piece. So this means that the piece will either exist or not exist, and the default engine that we create will have nothing. Let's see. So if we want to have, I'm trying to think of the API that the engine should exposed to the interface when it's being played. So where's the entry point and exit point here? I guess I can just start in the middle and then work it to either side if I need to. So one thing that I know that we will need to be able to do is to place the cursor. Which, this is the operation where the either the falling face has gotten all the way to the bottom, or the player has slammed the piece down. The next operation that will need to be performed is taking the cursor and placing it into the board. I think this is, yeah, if I conceptualize this correctly, this is going to have a lot of code paths that will present themselves as needing to be written. So this is a good one to go for. So placing the cursor can never fail as long as all of the other invariants hold. So this is another thing where I think it makes sense to trust the engine to only use this when it's appropriate. And then inside, in the debug builds, validate and make sure that everything is going okay. So here, we're going to debug assert some code that doesn't exist yet. We're going to say, in here, we need to make sure that the piece and the board don't have any cells that are overlapping. And we don't have any code written for that yet. I'm going to just keep that as a comment. What do they call them here? They call them cells? I guess they're just calling them filled cells. Then the next thing that we're going to do is place all of the squares from the piece into the board. Now how do we... So now this invites some discussion about how the actual squares of the pieces are represented. And the decision of that sort of falls after the rotation mechanics here. So one way you could implement this is to just have each piece is a grid of squares, and then it just says which ones are filled in and which ones aren't. I'm not a huge fan of that one. Another way that you could do it is have a sparse representation where you have a collection of an array of 4 cells, which are represented as coordinates, and those are offset from the center. And the thing that makes this tricky is that there's no center coordinate when it comes to Tetris pieces, because the O tetrimino. Yeah, there we go. Consistency. O and I are, I guess, what these are called. The O and the I tetrimino don't have a consistent center that they rotate around like the other ones do. And so those have a little bit weirder mechanics when it comes to rotating. And I think that given that we have that, there's not going to be a really easy blanket way that we can represent that. So it doesn't matter too terribly much. And the one that I instinctually go for is the sparse representation. So I think we should go ahead with that one. And one way that we could do this is to have an array of sparse representations and then use this enum to index into it, which is not very ergonomic and slightly error prone. So the way that I would prefer to write this, and this does have, I think, a little bit of a performance impact if the compiler can't translate this into a jump table, but I think it probably will be able to. The other way to do that is to have a function which performs a match operation over the enum and then returns a literal. And I'm pretty sure that it can optimize that into the same implementation as the array solution. So I'm going to say pub. What do we call this? Cells, which takes a immutable reference to self, a shared reference to self, and then returns something that represents all of the squares that are part of this piece relative to some origin. Now, if we want to be able to use this with for loops, the way that for loops are implemented is for loops tap into the into_iter trait. Into iterator, excuse me, which is a trait that's implemented on tons and tons of stuff. So if we want to be able to use this with a for loop for cell in piece.cells, then we would have to have it return something that implements into iterator. And I think, yes. So in a recent version of Rust, not terribly recent, but more recent than not version of Rust, they implemented into iterator for actual arrays, and they were able to do this because of the const generics implementation that landed. So I think here it makes sense to just return an array of coordinates. Now, whether or not it makes sense here to use usize depends on a couple of factors. In Rust, I know that there's a, I don't know if it's a guarantee, but there's an aspect of the compiler which says that any values that are 16 bytes or less are passed through registers and they don't hit main memory. So the representation of vector2, because it's repr_c, we know that it will always choose it won't insert any padding. So but with our power of 2 representations of integers. So here, the usize on 64-bit platforms, I should clarify, it's 16 bytes on 64-bit platforms and 8 bytes on 32-bit platforms. So because this is, I'm writing this for a 64-bit platform, it's going to be sorry, I got distracted. It's going to be 16 bytes, 16 times 8 times 4, because there are 4 cells. And so that's going to be 512. And so this is going to be too big to pass in just registers, and it's going to require a mem copy to go from one segment of memory to another. And we could get that down to 2 if we go to a yeah, thanks. Could get that down to 64 if we go for 8 bits. And then we could convert that from a U8 to a U64 on the other side, Or what we could do is have it return a U size, a vector 2 of U size, and then have that clone. And I'm a little bit more inclined to have that clone just for the consistency of keeping everything as a U size for consistency, not having to swap around types a whole bunch, over the smidgen of performance that we might be able to gain out of that by having that be a smaller size. So I think having this return a vector 2 of U size 4, because there are in piece, you implement an associated constant, const cell count is 4, because we have 4 here. Then we can say cell count in order to keep things readable like English. And then that returns that. So what we need to do in here is match self. Have it fill the match arms. And then here, this is going to be returning all arrays of 4 points. If I remember correctly, in the CGMath library, the vector 2 has a nice constructor, which is a lot shorter than writing it out as a struct literal. So I'm just going to say new for each of those. So now comes the question of how do we represent these coordinates? And I think it makes the most sense to define all of them as starting on the place where they rotate around, and then just having the I tetrimino be lopsided. So here, this is going to be 0, 0. Or, would it make it easier to write? Yeah, it would make it easier to write if we just gave it as a tuple. Then we do a little bit of fancy stuff here. Yes, okay, so in order to make this easier to comprehend, I think what we want to do is have these not actually be arrays of 4 points represented by vector 2s, but instead be tuples. Because here's the thing, inside vector 2, they have an implementation of the from trait. It says from any tuple of 2 numbers into a vector 2. And we will do it by reference because it's repr C. It will be able to just transmute the reference and then have them be the same in memory and just interpret the bytes as a different type. Type punning, very good. So that's going to be easier. The only thing that's going to actually screw up is that it will no longer return an array. It will have to return an iterator over some set. And because it's going to be iterating over something that's transmuted in place, all we have to do is have it be a iterator, which is a, yeah. Impl iter item equals a reference to a vector 2 of U size. So then here we can do 0, 0, 0, 1. Typing is hard. 1, 0. 1, 1. This is going to be iter, and then we map vector 2 from. No, I just do from because we'd have to specify the type for a reference to vector 2, which is a big pain in the ass. So this, we're going to do that one last. So, I mean, we don't really have to do the drawing tool just because we have the drawings right here in the design doc. The T is going to be -1. Oh God, we have to implement these as isize because they're signed. There we go. There's the complication. There's the secret complication. There's going to be -1, 0, 0, 0. Zero. Wait, yeah, there's 1, 0. Oh, rotation speed. Yeah, so next one is 0, 1. I believe that's the full T piece. L piece is, I'm defining these in terms of their north-facing representation here. So that's going to be -1, 0, 0, 0, 0. I'm gonna turn off that auto closing brackets. Never. Some people find that very helpful. I find it very annoying. So now when I type an opening brace, it won't do a closing brace automatically. So 1, 0, and then that is 1, 1. J piece is opposite. It's -1, 1, -1, 0, 0, 0, 1, 0. We get consistent spacing here. The S is -1, 0, 0, 0. Z being -1, 1, 0, 1. Zero, 0. Zero, 1. Or no, this is 1, 0. I think those are all correct. The I. I'm going to choose to have it extend in the positive direction. So what I'm going to say is 0, -1. Or it's no, -1, 0. XY. 0, all of the Y coordinates for this are 0, so it's going to be 0, 0. One, 0. 0. Oh, those aren't statics. Those are no, those are literals, so they should be static. Add a static type parameter, maybe? No, it still considers that temporary. Oh, it would... Okay, we make it static. Because it moves that into the iterator, and it would be static if we returned a reference to it, and then that is a reference to static memory. If you are returning static stuff and if you're returning a reference to static stuff, you can always add a static annotation to the reference, which won't ever hurt your API's coverage. It will only allow people to do more with your data if they know that it's static. So it's a good thing to add if you're returning references to static data, which gives the caller more freedom to do stuff with it. So here, because normally what this would do is it would infer the lifetime of the returned data to be the same as the lifetime that borrowed itself. So you would artificially restrict the reference to the static data to the lifetime of the piece kind that you borrowed. So here, it wouldn't make too big of a difference because it would be, all of these are static, but it's a good practice to get into to try and make your APIs as wide as possible. So here, now we have access to all of the V's. What do we need to do then? Oh, yeah, we need to be able to rotate. So we're not actually, here we're not taking the rotation of the kind of the piece, we're taking the rotation of the piece that's inside the cursor. And this actually has a position and a rotation. So we're going to need to rotate the coordinates that come back from this and then shift them by the position of the piece. So we won't be calling cells on the kind, we will be calling cells on the piece. And this will be always privately accessed by the piece class. So it's not actually a class. Don't tell any Rust developers I said class just there. Pub cells. Self turns and impl iterator. Item is no longer going to be a static because we need to manipulate it. So this is going to be a temporary that we create, but we're going to be moving it out because it's a temporary, and so that gives us more freedom. It's going to be a vector 2 of use size, and we're going to need to handle some error conditions in here. And I think it will be sufficient to... No, it won't be sufficient because we will need to be testing pieces that we move outside of the bounds. The error condition that would occur here is if you have a piece that you're trying to move to the left, and that would push some of the cells out of bounds. That would mean that the coordinates for those cells would actually be negative. And given that this is a usize here, which means unsigned size determined type, that is unrepresentable here. It would present itself as an integer underflow, and that's not technically it would work, but that's not what we want if we can avoid it, because we want to reserve this to all like clearly defined behavior of the things that are happening. So here what we want to do is we're going to return we could either return an option of the iterator, or we could return a result. And the thing that drives this decision is if you want to actually put meaningful error information. If there's only ever one kind of error, using optional is perfectly acceptable, because you can just document the error in your documentation and it doesn't contain any information, and so it's just always constant. But if there were different types of failures, you would want to represent that as a result. And I'm pretty sure that this is only, we don't really care if it's out of bounds to the left or to the bottom, or to, I guess we could also implement bounds checking here. Yeah, I don't think we can always change it to a result later. I think an optional is fine. So if this is out of bounds, if this has cells that are out of bounds, it will return none. Yes, but in order to check if we need to push it, we need to see if it's out of bounds first. So this is going to show if the cells of this piece are out of bounds. And this piece is going to be representing a state that the cursor could be in. So here we're going to return an option of this iterator type that will be, there's an existential type, so it will be determined at compile time by the compiler. So, currently complaining because we're returning the unit implicitly. If we want it to actually perform the type checking to see if there are any other problems, what we can do is just put a to-do here. And because to-do is a divergent function, it will automatically coerce to the type that we want. Cannot resolve opaque type. This error will resolve once the item's body returns a concrete type. Very good. Okay. This return value is of diverges. All right. That makes a lot of sense. Cool. So, here what we need to do is take the cells of the kind, so self.find.cells, this is an iterator which vends references to a static array of vector 2s, and we want to perturb them by the rotation. And so here what this is we're going to need to multiply the vector by the rotation matrix corresponding with the rotation. So here what we can do is say we can add a new function to our rotation representation. Matrix, which takes a shared reference to self and returns a we could do that. We could have it compute a rotation matrix based on the 90-degree rotations, or we could implement it ourselves, because we know that all of the rotations that we're going to be doing are 90 degrees, we know that all of this is representable with integer math. And I think that might be a more optimal implementation than trying to compute a floating point rotation matrix. So what this would actually be is we can pull a trick and make it behave as if this rotation were a rotation matrix. And so normally where you would multiply the point by the rotation matrix that you want, we can just multiply it by the rotation, and then it will do the same thing. And so in order to emulate that, we will implement the multiply trait Stood ops mul, I think it is. Yeah, stood ops mul. We will implement the stood ops mul trait, which is the thing that gets invoked when you use the multiply sign, for rotation. But the thing that we're going to do, this defaults to multiplying a rotation by a rotation, but we can make it a separate trait. These traits are generic. We can make a separate trait for multiplying by, or no, we would implement this on vector, right? Yeah, multiply by a rotation for vector 2 of S, where S is base num and all those things. Or what do we actually need for this? We need S, which is something. We'll do that when we get there. So we multiply a vector by a rotation, which consumes the self, I think. Yeah, it consumes the self. We can have it autofill this. I'll have it autofill. So we have a type output, which is a self. We return the same type that we put in. And so in order to multiply, I don't want this to be called RHS. I want this to be called rotation. We're going to match the type of rotation. Have it autofill the match arms. And rotating to north is a no op. So we're just going to return the same thing that we put in, which is self. Rotating to south is 180 degrees, so it will flip. That's the same as flipping both the X and the Y axis. Right? We have this, and we want to make it this. We flip there and there. Yes, so we flip both the X and the Y axis. So we make a new vector. I think I might do destructuring here. So we do let vector 2 X, Y. Well, then we can't do the nice. Then we can't do the nice thing of returning self. I'll just do it the normal way. So we have vector 2 new of minus X minus Y. And so here we know that our, this needs to be, why won't it let me multi-click? Oh, it's my window manager. Never mind. Self.x, self.y. Cannot apply unary operator minus to type S. Here's the thing that we need. So we need to constrain S so that it can be negated. And that is currently represented in the standard library by stood ops neg. So we need to constrain it so that S implements neg. And that's not in scope, so we do stood ops neg because I don't need to implement that. I don't need to import that for the rest of the function. It can just be in here. So S is stood ops neg. S as stood ops neg output. We need to make sure that the output is self. We only want to be able to negate vectors with internal representations where negating the type does not change the type. So I'll move this to a where clause because this is getting a little bit much. Is that... I'm trying to figure out if this is... Ops... Is this output? Yeah, output equals... S. That's what I want. So now this can be negated into itself and produce the same vector that we put in. So east is just a 90-degree rotation. So what that is the x coordinate becomes, the x and the y switch places. Right, let's see. Okay, now it's math time. If we have the coordinate 1, 2, and we want to rotate it 90 degrees, the x coordinate becomes the y coordinate, and the y coordinate becomes negative x. Y coordinate. So in order to rotate by 270 degrees, I could just break out the paper. That's true. Let's see. So here, if we've got our we've got our axes that are here. I can draw it up. If we've got 0.23, and we wanted to rotate it 90 degrees this way, it would become here. And so that 2.3 becomes 3, -2. So that was, yeah. The x is what x becomes what y was. And if we wanted to rotate it to here, which is the no, it's all the way. It's rotate it by 270 degrees. It's the same as rotating it that way. And so this becomes yeah. Y becomes X. X becomes -y. And then these are all self. And we're doing partial moves out of self, but it doesn't matter because we're not reusing the parts that we move out of self. So here, what we need to do is multiply the thing that came out of the, so we're doing for each cell, we're saying cell, we're multiplying the cell times the rotation. So one thing we could do here if we wanted to Rotation matrices wouldn't necessarily have been more complicated. It would have just been a bunch of unnecessary work for the computer to do, because what it would have to do is take the trigonometric function to figure out the sine and cosine components of the amount that we wanted to rotate, and then it would multiply the result of those to... We would convert the existing coordinates to floating point, multiply it there, and then have to convert back to integer, because that would support partial rotations, whereas here we're only worried about rotations in increments of 90 degrees. And so here it's not necessarily less complicated, but it's more straightforward, and it's more representative of the operation that we're actually doing. And if we want to be kind of fancy, what we can do is have a private method which returns a function that will rotate. So if we want to say rotator, self returns a impl of, takes a vector2 of u size and returns a v size. I'm real close to just defining vector2 of u size as, I think I will. In the engine, I'm going to create a type alias, which says that a coordinate is just a vector2 of u size. So here we can just say, we can do a find and replace for yes, this is still stream beats. This is the Lone Wolf album. And I will need to find a new album pretty soon, because we're at the end of this one. All right, so our engine's coordinates are now set to be a vector2 of u sizes. So now we can use that type alias to make our code more straightforward in all the places where we work with coordinates. But we need to import our definition first. Oh, another thing that we should do over here is define a new type alias offset, which is a CG math vector2 of I size, so that we have nice matching stuff and we don't have to still import it in other places where we're trying to compute an offset. We can just use our own type alias. So here I am returning a function, a static function type, which, oh, that's really loud. we're returning a function type, which here we're going to have it actually do the rotation here, and that's just going to be our rotation implements copy, right? No, it doesn't. Okay. Derive, clone, copy, partial leak, debug. The big four. And then here we don't need to futz with this anymore if we know that we're only ever going to be working in vector 2 of I size and U size. So we can just say, we can do a more constrained implementation where we're only ever rotating offsets. And we don't have to have that constraint there because it knows from the concrete type. And so here what we want to do is copy out. I'm going to do, and then the rotation of that coordinate is just going to be, or no, this is an offset. Let's say self.rotation, and then if I transform this into a move closure, it will automatically copy out the rotation. So if I don't have this move here, what happens is this closure tries to take ownership of the reference to self. And then it has this problem where it captures the anonymous lifetime that we defined for self. But what we want to do instead is clone this rotation object and then move it into this closure so that the lifetime is static and we know that it's not bound to any other data that lives elsewhere. So I think by defining it as a move closure, no, because it still tries to close around self. So what we can do here is say let rotation equals self.rotation, and then that forces a copy because this is a rotation, and then we can move the copy in here, right? Let's see. What is it complaining about? Oh, that's why. There we go. That solved it. I was accidentally still explicitly capturing self. Oops. Yeah, now we're good. So then we produce, what this does is it produces a rotator function object, which represents the rotation of the current cell's rotation. And then we map that across all of the cells that were returned from the initial positions from this kind cells method. So after that, what we need to do is offset. So we'll do a similar thing here where we'll say from offsetter self impl or I guess we could call it a positioner because we have a type offset. That could be confusing. I guess we don't need this move here explicitly. It'll no, we do. Okay, yeah. Position is not a coordinate, it is an offset. This is the kind of thing that Rust makes you think about. So now what we do is map self dot positioner. And then what we need to do is try to convert okay, here's the thing. We can't return an iterator from this. We need to return an array of 4 cells. Because what we need to do is process all of this arithmetic completely to know if any of the cells are out of bounds. And if we return an iterator, all of that is lazily evaluated, and so we don't actually have an indicator of... We could ask for an earlier cell if, even though a later cell would be out of bounds, but this would return it anyway. And so what we need to do is eagerly evaluate all of that logic. And so here that would be returning a collection of the coordinates. And we could either return a vector allocated on the heap, or we could return an array. I'm more inclined to return an array because it makes a static guarantee about how many items there are, which is less wiggle room and less room for error. And so what we're going to do is have a coordinate 4 per cell count. And then I think, do arrays have a map method? Array map. Yes, they do. Part of const generic's landing was that we now have a map method directly on an array, which means that we don't have to do any bounds checking. We can just map directly from one kind of array to another. So here it actually makes more sense to return an array because... yeah. Ugh. Piece cell count. And so then we just map the from vec, or we map an offset from, and that will automatically map those. Yes. This should optimize really nicely. And then mismatch types. All we've got is mismatch types now. Okay, so we've got our offsets. All of that mapped. So we've mapped it through the rotator, or we've mapped it through the positioner that we constructed here. Did my can get green screen? Oh, it must have, because it's blue. That's funny. Yeah, so here we've got an array of 4 offsets. And we need to return an array of, we need to try to convert that into an array of 4. And I believe, let's check, does iSize have an implementation of try into, no, that's just the blanket. Is there is usize have a try from iSize? Where are we? Try from iSize. Yes. All right. So I think if array then has a try from, there's a try from slice. Does it have like a try map? No. This may be maybe a sticking point. We've got an array of offsets that we need to convert into an array of coordinates, but we can't. The standard library doesn't provide a nice method for converting with the try from trait, like a lot of other aspects of the standard library do. So I don't think if we just said try into, I don't think that would work. Because trait bound is not satisfied. Yeah. I think we may have to actually just do this with a for loop. So then I say let coords equals an array of 0 and I say for offset in offsets dot zip, or offset chord in offsets dot zip with the immutable reference to chords. What this will do is it'll create an iterator, which is a pair of offset, which is an offset, and then chord, which is a mutable. Oh, that needs to be a coordinate. And I believe it has 0 value? Let's see. Zero. Yeah. It implements base num 0 with a function 0. But I have to use CGMath 0 for that to work. All right, so I'm doing something that's a little bit BS here. What is it complaining about? Let's see. Ah. It's my favorite Deadmau5 song, Some Chords. Array zip, okay. Wait, why does that still need array zip if I'm explicitly calling in... Aren't all his songs some chords? I mean... He's got some songs that only have one chord. So this, I think, this construct needs a, yeah. I'm using a nightly feature here, which should be stabilized at some point. Called let else, I think. Yeah, and what this allows is a very specific thing. Right? Oh, hold on. There's a new syntax here, which allows matching partially, sort of related to if-let, but what it requires is that it will use the it doesn't want to... Oh, I can't do that. Never mind. Never mind. I was going to do it, but I can't. There's a new construct which allows you to do a partial match and then a pattern match on this side. So if I was going to do some and then... this would try and match against this pattern, and if not, then it would execute the diverging block put in the else. But because I need to... I'm not defining a new variable. I'm inserting into an existing one. I can't use this because there's another feature which allows you to assign into patterns, I think, but that's not, I don't think that's anywhere near stabilized. So what I'm going to do here is an explicit match. I'm going to say match try into, and then on the OK case, I'm going to return the chord. And then in the error case, I don't care about the error, and I will just return none from this whole function because that's there. Offsets into iter.zip. Unless array zip is nicer, at which point I'll use that. Array zip. Zips up 2 arrays, so I would have to pass in the array. Yeah, I won't be able to use that here because I have to pass in a mutable reference, or an iterator of mutable references instead of an iterator of values. So I am going to say into iter and then zip that with mutable coordinates. So then what I have here is a vector tree of I size. Why can't I try from? From is this not correctly? This should only require try from vector 2. That shouldn't require from. Is this a bug? I hope not. Oh, it doesn't implement. It only implements it where it's an infallible conversion. Well, that's inconvenient. I'll work around that though. So I think probably what I want to do is explainable. This is kind of So the trait try from executes fallible conversions between two types, and normally what you do is you try to convert each part, and then if any of it fails, then you return a failure. But here in the CGMath library, they've implemented try from on the vectors, but only where each thing can be infallibly converted, and then the only error that they can return is infallible. Oh wait, no, here. I'm blind. They implement... No, they did. Okay. Yeah. They basically only allow infallible conversions because they require into and not try into. So all I have to do is just handle the errors myself. So what I'm gonna need to do is say in these offsets, I'm gonna say offset X, Y, and then that's gonna pattern match in. And then I can match on the tuple of it is a really weird choice on their part. I'm gonna pattern match on each component try into. I'm gonna let it derive the types try into, and then I'm going to say only if it's a tuple of okay X, okay, Y, then I'm going to say coordinate new coordinate X, Y. And anything else, which it would include at least one failure, and then in that case I'm going to return none. And then this coordinate gets assigned into the slot, which is being iterated over by this here. And I don't think I can actually... Oh no, I need to just declare it as mutable so that it can be assigned into. And then that should go. And if we wanted to write a unit test for this, config test, make sure it only gets compiled when we are running tests. Use super. And then we rotate S. Where's our design? So I want to try and rotate the S to, or this is going to be S piece positioning. So if I say S is a piece with a kind of S, a position of which is an offset. For the X and Y offset, let's give it like a 5/6. And then our rotation is... Put those in the declaration order here. Just cause. Let's say it's a west. And we want to validate that assert equals s dot, what was it? Cells are equal to I didn't do any bounds checking here. That's right, we were going to do additional bounds checking in here to make sure that it was inside the map. So I'm gonna probably do another match. I'm gonna say, because we've already converted it to an unsigned type, since we already converted to an unsigned type, that means that we don't need to check the negatives out of the matrix. My question now is, do they declare the top left or the bottom left as the 0 coordinate? The bottom left corner of a 10 cell wide by 20 cell high matrix is considered the origin. With the first cell being at X coordinate 1 and Y coordinate 1, I guess that's so that they don't have to handle negatives. Interesting. That's an interesting solution. I'm going to choose not to do that, just because that's kind of gross. So what I am going to do is check and see if each coordinate is within... I think what I might do here is have an associated function of the board type. There we go. So I've destructured the coordinate that's passed in into its X and Y components, and then I'm individually checking if X is less than the width that we declared and Y is less than the height that we declared. And because this is a zero index system, we can just use less than instead of less than or equal to. Yes, I am deviating from the design guide in a place where I very much disagree. So here what we can do is just say board dot, no, board contains, what did I name it? Inbounds. And then, oh, I guess I have to do, yeah, I'll put it in the loop because I just do it all at once. Okay, cool. So we say, no, I'll remember. And here I can also use the let else. What's the this is the RFC, but where's the tracking issue for this? Rest issue. There we go. Feature let else. That's what I had. Yeah. And now because I'm declaring a new thing, I can just say let or no, because I still have to destructure. Never mind. Okay, yeah, I can do let new equals match. And then I say if, or can I incorporate it easily into this? No, I don't think so, because I have to do actual operations on the numbers before. Yeah, I'm gonna have to do a completely separate check. Okay, if board inbounds new coord equals new, else return none. Now we have the fall through. It would be nice if they just implemented this for me, but they chose not to for some reason. But here we can say we're asserting that an S at that position with that rotation is, and then here we can just do that array map trick again. But I want to say if S cells now to actually do the hard part and compute what this is supposed to be. So the S starts at -1, 0. So first thing we need to do is rotate it. So if we're rotating it to be west, that means it's going to be this, which means it's going to be -1, -1. -1, 0. Oh, the ordering. Yeah, it needs to start at the top, so that's going to be 0, 1. 0, 0, -1, 0, and then -1, -1. And then we need to actually add 5 and 6. So then that's going to be 5, 7, 5, 6. Yeah, 6. And then 4, and 6, and 4, 5. Why is it complaining? Where did I forget it closing something? Let's see. And that should match there, but it doesn't for some reason. Ah, I forgot the opening brace here. Cool. Cool, let's run this test and see if it passes. It doesn't. I made a mistake somewhere. Most of these are, I'm much more willing to say that I type these numbers in wrong, because 2 of these are right. If you go by individual numbers, I got a 3/4 right. Let's see. It's the Y coordinate. And because this starts here and then it rotates and rotates and rotates, that's going to be -1, -1. Right? -1, -1. So that should be 4. All right, I gotta check my math. What the fuck did I do? I did it in the wrong order. That goes here, which is -1, 0. The third one is 0, 0. If that's the order that I declared it in. Is it? Let's see. This is the real work of programming. Oh, I was looking at Z. Oops. -1, -1, 0, 0, 0, 0, 1. Then if we add 5, 6 to this, that becomes 4, 5, 4, 6, 5, 6, and then 5, 7. Right? No. Hey, it worked. Okay. Cool. So we've got cell positioning and rotation computations working to a point where I'm happy with it. From there, we can very easily say for cell in we only ever, here's another invariant. We can only ever call place cursor, just like we are asserting this, the bag is empty. We can only call place cursor when the cursor has a piece in it. Otherwise, there's nothing to place. And so normally we'd rely on the calling code to only call this function when the cursor is there. But inside, because of the way that Rust is, we are being forced to actually check for that. And so there's going to be a runtime check here that may or may not be optimized out, but it's very small, where we need to actually get the piece out of the optional. So here I'm going to say let piece equals, or let cursor equals self.cursor.expect. We're expecting it to be there. Otherwise, called place cursor without a cursor. And that's going to crash the application if that condition is not met. So now all we have to do is for cell in, I guess we want to do as ref because, or no, we want to consume the cursor here, so we need to move it out. And so what we actually want to say is self.cursor.take, which removes the value from the optional and gives it to us by value here. So then we can say for cell in cursor.cells, we're going to debug assert, make sure that the calling code did this right. We're going to debug assert that the board at that point and what we want to do is, because this is a linear array of size, we need to make a new accessor. And get self returns an option of, no, returns the contents of the thing, which are bools. Returns a bool, otherwise it panics, and so we say, or I guess we do optional. And if it's out of bounds, then it returns a none. And say if, and we're going to get at an x and y. Or get at a coordinate. There we go. Consistent, strongly typed API. If we're going to assert, no, we need to say if because we're doing an optional. If x, we can do this a different way. We can say inbounds coordinate then, because in the standard library, where's our standard library? Here it is. In the standard library, there is a function on bool, which is called then, which takes a function and returns an optional of the result of that function only if the bool was true. So we say self inbounds coord, then it's like a if then. Self.0 at chord.x times chord dot, no, it's chord dot x times self width plus, no, chord dot y times self dot width plus chord dot x. I might pull that out into a yeah. So if we have a function which takes an x and a y, takes a coordinate, and then it returns an index. Function indexing, which takes a coordinate xy is a coordinate, returns a use size, which can be used to index into the array. It's going to be the y coordinate times the width, which represents the number of cells that were passed to get to that y coordinate, and then plus the number of x to get to the one that we're looking for. So that's that's y times self width plus x. And so here what we say is self 0 at self dot indexing chord. Right? Oh no, that's a static method, so it's going to be capital self indexing chord. Cool. So that will return an optional sum of the cell at that position if it's in bounds. That get cell, which is a coordinate, not an actual cell. We can just say first of all, we need to there's something. Thank you, Rust, for making me check if all of the not only if any of the coordinates are already filled, but also that they're all within the bounds of the thing. So we're going to say debug assert. No, we're gonna say coordinate equals cell. No, reference to the cell. That should not return option of bool. That should return an option of the actual, a reference to the cell inside the board. So we return a reference to the cell inside the board, not copying out the value. So we say the cell, which should be a reference to a bool, should be self.board.get at chord, and then if this currently fails because this is the wrong type, this is an option, and so what we need to do is unwrap this and say expect cursor was out of bounds. Oh, this is cursor.cells.expect. This is going to return, or we already checked that. Yeah, so here we move this expect here. Cursor was out of bounds. And then here we can change this to just an unwrap because it's checking the same thing. that'll just get it out, and then that will never happen. And if it does, then it'll crash, and I'll know exactly where it is, and know we can look at this code and see exactly where it was supposed to have checked, and then find out what's wrong from there. So now this is the right type. And say, so we want to, now that we have this reference to a bool, we can debug assert, trust but verify that equals the value at that coordinate is false. It's not filled in. And then from there we can, oh, we need to use that again. Never mind. Move this out and say let oh shit, we need this to be mutable. Get. So we transform this to get mut. And mut self coordinate self inbounds, then amp mut self at 0. Now it's a mutable reference to the bool. Now we can change it. So let cell, which is supposed to be, double check, mutable reference to a bool, equals this get mut unwrap debug assert cell. The value in cell is false. Now we say the value at cell equals true because we're placing a piece into there. So now we've taken the cursor, made all of the places underneath true, and now we can exit. And so this would then place the cursor at the appropriate point. And I think that's probably how much progress I want to get done for today. We've done a good job of defining a lot of the base for this project. I'll probably have another stream pretty soon where we keep working on this, because I think implementing Tetris is a really interesting problem. There's a lot of cool things that you can do and a lot of interesting ways to model the domain. So yeah, I'll be back. Thanks for joining.